look at this subtopic, equipotential. First, we have equipotential surface. Equipotential surface is also called equipotential line. Okay, so let's write down here first. This is also called equipotential line. From the name, we know that they have the same potential, okay, electric potential. So what they said here, a surface where the electric potential is constant. So to understand equipotential surface, so let's look at this picture. So the equipotential surface is the green color dotted line. So this is equipotential surface, or you can call it equipotential line also. So what happened on this line is, along the lines, the electric potential will be the same. So for example, let's say the electric potential here is 3 volt. So it will be 3 volt all the way along the line. Okay, so that is equipotential line or equipotential surface. Now let's see the next point. Equipotential lines are drawn such that potential is constant between intervals. Okay, so what is meant by this? Now let's say I give one example. I draw electric plate here, and here is the positive terminal of the electric plate. The other side is the negative terminal of the electric plate. Okay, so I put, let's say I put 4 lines in between. With equal distance from each other. Okay, so equal distance from each other. Okay, now let's say I put the electric potential for this case. Electric potential, let's say here is 20 volt. Then the other side will be, let's say, negative 30 volt. So the potential difference is hence 50 volt between the two plates, where we have to minus the two values to get the potential difference. 20 minus with negative 30, so we get 50 volt as the electric potential. So the equipotential surface or equipotential lines are drawn such that the potential is constant. Potential is constant, that means it's like this, they have the same difference. For example, this is negative 20 volt, negative 10 volt, 0 volt, 10 volt, and then 20 volt. So their interval make constants. Okay, that means that we have a fixed increase. Okay, from here to here, fixed increase of 10, and then another 10, 10, 10, and 10. Okay, so the second point is trying to say something like this. Okay, so let's draw an arrow here. The second point, it means this one, this one, this one, this one. Okay, so third point, as potential constant, the potential gradient is equal to 0. Hence, E along surface is equal to 0. So E is the electric field strength. So electric field strength is equal to the potential gradient. And because along the equipotential surface or equipotential line, it has no change in electric potential, and hence the potential gradient is 0. And because potential gradient is 0, then the electric field strength E is also equal to 0. Okay, so meaning that if you move along the equipotential line, so that is 0, that is 0, 0 electric field strength, 0 electric field strength. So that means the first of all, we have to know that the electric field strength, right, is actually force per unit charge. Okay, try to imagine that electric field strength is force per unit charge. So in this case, when the particle is moving along the equipotential line, the electric field strength is 0, and that means the force is also equal to 0. Okay, so now let's look at the next point. Hence, no work is done when a charge is moved along this surface. So how can this happen? Work done is force multiplied with displacement. So because there is no force, so work done is equal to 0, as there is no force. Force times displacement, force is 0, hence work done is 0. Okay, so next point at the bottom, electric field line must meet equipotential surface at right angles. So what is electric field lines? It is actually the red color lines. From positive, it goes up and go into the negative charge. So it is 90 degree. So as you can see, let's say I mark it here, 90 degree. Okay, so you can see it is 90 degree with the equipotential surface. Spacing will be closer when field is strong. So that means, for example, when you see the red color arrow around the charge, you can see many arrows, meaning that the field is strong around here. But if you pull it far away, so you will see this region have less number of lines, meaning that the field is weaker. Okay, so even for electric plates, we can draw the electric field lines, so which is from positive to negative. So the electric field line is like that. It is perpendicular with the equipotential lines. Okay, so now let's move on with 7.6. 7.6, similarity and differences between electric and gravitational potential. So the first one, similarities. Ratio of work done to mass or charge. Okay, so that means if we look at gravitational potential, where the symbol is phi, so gravitational potential is actually work done per unit mass, whereas electric potential, the symbol is V. So V is actually work done per unit charge. Okay, so they are similar in that way. They are work done divided by something. Now let us look at the next similarities. The second point, as you can see here, work done moving unit mass or unit charge from infinity. So this is actually the definition of gravitational potential. So gravitational potential is the work done in moving a unit mass from infinity to a point, whereas the definition of electric potential is work done in moving a unit charge from infinity to a point. So the second point here, what are they trying to say is they have the similar definition. Yeah, it's definition. The next one, the third point, both have zero potential at infinity. Okay, now let's see, both have zero potential at infinity. So first of all, we have to know that for gravitational potential, the formula has negative in front. It is negative gm/r. But for electric potential, the formula is q over 4 pi epsilon naught r. So it is positive or negative. It depends on whether they are light charge or they are unlight charge. So if they are light charge, they will repel, then they are positive. If they are unlight charge, they will attract, then it is negative. Okay, so let's say for gravitational potential, the graph is like this, phi versus r. The graph is like this. For v versus r, the graph is like, it's positive. So I change the axis, put it down a bit. It's positive. Okay, so no matter which graph are we referring to, what can we see here is when it is infinity, the gravitational potential is very close to zero. Likewise, when it's infinity, the electric potential is very close to zero. So that is the similarity. Now we look at the next one. Differences. So the first point, gravitational forces are always attractive. Okay, always attractive. So that's why the phi has a negative there. But electric potential can be attractive or repulsive. So this one we discussed just now. That's why the next point you see, electric forces can be attractive if they are unlight charge, or repulsive if they are light charge. Okay, so for gravitational, work got out as masses come together. So first of all, what is meant by work got out? So we have to know that work got out means work is negative. To understand this, we have to look at the graph. So where if you put the masses together, you have to move the graph in this way. Follow the blue arrow that I put over there. Okay, so you can see the R is decreasing when you put the masses together. And when the masses come together, the gravitational potential is getting more and more negative. And you know, gravitational potential is actually work done in moving a unit mass from infinity to a particular point. So what am I trying to say is gravitational potential is actually work done. So if the gravitational potential is getting more and more negative, that means the work done is also getting more and more negative. That is what it means by work got out. Okay, so you refer to the graph to understand it. Okay, so which is this part. The phi is getting more and more negative. Now, next one. For electric, work done on charges if same sign. Okay, if same sign. So meaning that you refer to this graph. So I label it first. When they are same sign, we use this graph where they repel. and they say work done. Work done means W is positive. W is positive. So to understand this, we have to put a blue arrow in this way. The R is decreasing. That means the charge are getting nearer to each other. So you will see that the electric potential is getting more and more positive. And you know electric potential, the definition is work done. So if electric potential is getting more and more positive, that means the work is done. W is positive. Okay, now next point, work got out if opposite sign as charges come together. So we have to know that if the charges have opposite sign, so meaning that they are attracting, and if they are attracting, their graph is in this way. So this is where the charges has opposite sign, and when the charges come together, so we follow the blue arrow, the R is decreasing, the V is getting more and more negative, and V is work done. Hence the work done, I mean the work is negative, and we call it work got out. So again, work got out, that means W is negative. Now let us look at the question here. Question 6. State one similarity and one difference between the electric field lines and the gravitational field lines around an isolated positively charged metal sphere. Okay, so first we are going to talk about the similarity. So we can write lines are radial. Okay, this is the first option. So if you don't want this, you can say greater separation of lines with increased distance from the sphere. So this is the second option. Difference, so we have to say gravitational lines directed towards sphere and that means it's attractive. Okay, and electrical lines directed away from sphere. So it's directed away from sphere because this is a positively charged metal sphere. So that's why the electrical lines are directed away. So let's look at part B. A positive point charged positive Q is positioned at a fixed point X and an identical positive point charge is positioned at a fixed point Y, as shown in figure 6.1. So meaning that you have positive Q at point X and positive Q at point Y. They have the same charge. So continue here. The charges are separated in a vacuum by a distance of 10.0 cm. Points A and B are on the line XY. Point A is a distance of 2.5 cm from X, and point B is a distance of 2.5 cm from Y. The electric field strength at point A is 4.1 times 10 to the power of negative 5 volt per meter. Calculate charge positive Q. So to calculate the charge positive Q, we can make use of the information given, which is the electric field strength. So electric field strength, this is electric field strength at point A, which is 2.5 cm from X, okay, from X. And at the meantime, it is 7.5 cm from Y. Okay, so this point charge will have force on point A in these directions, and this point charge on point Y will also have force on point A in the opposite direction. So let's say I label it as F2. As we know, force are vector quantity, so if they are acting in opposite direction, so when you want to find the net force here, then you have to take F1 minus F2. So why we talk about force? Because our electric field strength is force per unit charge, so it's related to force. Okay, so the 4.1 times 10 to the power of negative 5 here is something like the net. After you minus, you get 4.1 times negative 5. So we have to take the charge. By the way, the formula E is equal to Q over 4 pi epsilon naught R square. So as what I said, 4.1 times 10 to the power negative 5 is the net force, or the net electric field strength. So we have to take the electric field due to the charge at point X minus the electric field strength due to the charge at point Y. Okay, so let's work it out. 4 pi epsilon naught. The R is 2.5. Pi epsilon naught. The second fraction here is for point Y, so it is 7.5 cm away from point A, so that's why I put 7.5. and then you have to work this out and get your Q. So you may factorize the Q first. For pi epsilon naught, then what remain is 0.025 square minus 0.075 square. So you can work out Q, and you will get 3.2 times 10 to the power of negative 18 coulomb. So next part, on figure 6.2, sketch the variation of the electric field strength E with distance D from A to B. Okay, so we already count at point A the electric field strength. Sorry, it's not counting, and this is given. The electric field strength is 4 times 10 to the power of negative 5. So because of that, so we have to put a point over there, and after that we have to understand that the more you go to point B, then the the electric field strength by point y will be greater and greater. Okay, so meaning that you have to know that the electric field strength by point y is a negative value. Okay, it's a negative value. So when they reach point B, right, you should expect it to be negative value, which is same magnitude, 4 times 10 negative 5, but it is negative. Okay, it is negative 4. Okay, so and after that, in between it should be equal, and hence end up with 0. Electric field strength is 0. And should we draw a straight line or should we draw a curve over here? So I have to say that we have to draw a curve. Okay, we have to draw a curve instead of a straight line. After all, you look at the formula, it is not of the straight line form. Okay, so we draw a curve in this way. Now let's look at part 3. A small positive charge is placed at A. The electric field causes this charge to move from rest along the line AB. Describe the acceleration of the charges as it moves from A to B. Okay, so first of all, based on the graph, I have to say that the electric field is decreasing. It's decreasing. So electric field is actually the force. If the force is decreasing all the way until here, that means imagine based on force equal to ma, right? So the acceleration should be decreasing. Acceleration should be decreasing until it becomes 0 at this point. Okay, so we write this out first. Acceleration decreases to 0 at midpoint. Okay, then after that, what happened is the electric field strength become negative, meaning that the force is also getting negative. And based on our formula, F equal to ma, resultant force equal to ma. So if this is negative, then acceleration will be negative also. Okay, so what happened here is you can write your second part in this way. You can say that then acceleration increases. In terms of magnitude, is getting greater and greater, but it is in the opposite direction. So in the opposite direction. So to understand what happened here, of course the second point, acceleration increases in the opposite direction. You can also call it negative acceleration. Or in other words, deceleration. Okay, so it means what? So let's see the motion here. The positive charge move from rest along the line AB. Okay, so initially the acceleration is quite big. So let's say, for example, I put value. So let's say they start from rest, the velocity. Okay, then it increased a lot in 1 second. Let's say in 1 second it becomes 30 meters per second, for example only. So there is an increment of 30, and then after that, example again, at the second, so let's say the acceleration decreases already. It doesn't increase that much. It increased 20, let's say. Increase 20 and become 50 meter per second. And then at 2.5 second, there is no more acceleration. So let's say at 2.5 second, it becomes 60 already. Okay, so let's say this is t equal to 1, this is t equal to 2, this is t equal to 2.5. Example only lah, 2.5. Okay, let's say become 55. Okay, so what we can see here is the first part in the note is all this. The acceleration decreases. Okay, so that means the increase in velocity getting lesser and lesser. But bear in mind, the positive charge is getting faster and faster. And then after that, this is the first 2.5 seconds. So after that, you should expect it to decelerate as the resulting force is negative, so it will decelerate in the second part. So let's say something like this. Let's say initially it decreased by, let's say when they reach t equal to 3, so let's say decrease by 5 become 50, and then decrease more to 30 at t equal to 4, and decrease more to 0 at t equal to 5. So this is the second part. So where the second part is in green color, so in terms of graph, I circle up this part. So this is the second part. Deceleration happened. Okay, so settle for this chapter.